Thanks very much, Jack. Thanks all for coming. It's really a privilege to speak at this wonderful workshop. Thanks to ICTS for organizing. All right, so I'm going to tell you about a problem falling generally under this category I call empirical measures. And I've listed some related works either in FPP or in related models that address versions of this question. And let me pose it to you in kind of a picture, and then we'll get to the precise details in a moment. All right, so in a picture, suppose this is the geodesic, and suppose we're going from 0 to any one. Suppose this is a geodesic, it may not be unique. And suppose I can take one of three types of weights. I call them, just to be unprecise, low, medium, and high. Okay. Well, because we're talking about first passage percolation, I want to take many low weight edges. So I could see, I could count, there's, I think, 8 low weight edges on here. And then maybe the blue, right, is somewhere in the middle, it's medium. I take 4 of those, and the high, those cost me a lot, so I only take 2 of those. Right? So I could draw some histogram of how many lows, how many mediums, how many highs. And of course, this generalizes to continuous distributions. I don't have to have discrete weights. And then I could have some continuous histogram. Right? So the question is, does this histogram converge to some shape as I send n to infinity? I take a geodesic between 0 and some point very far away. Then I want to know, is there some right balance between low, medium, and high weight edges? Or if you have a whole continuum, if your support of the edge weight distribution is all of the non-negative numbers, then I could have this extending all the way to infinity. And I want to know if there's some limiting shape to this histogram. So that's the question in words. Okay. All right. So I'll get to making this a bit more precise. First, let's just make sure we're all on the same page with notation. So I'm talking about first passage percolation, as we've been learning about on ZD. I take IID edge weights. So you can maybe generalize much of this to stationary and ergodic, but let's not worry about that. Take IID edge weights, TE, and this is something we haven't talked about. I'm just going to actually give an explicit name to the law. So I'm going to call the law this script L. So that just refers to the measure on the non-negative numbers that says this gives me the probability measure associated with these TEs. Okay. And I'll also additionally make the assumption, as we have been doing often, that the probability of taking a 0 weight edge is less than the critical probability for Bernoulli percolation. So this just keeps us within the realm of subcritical percolation. Again, much of what I say has versions in critical or supercritical. Well, let's just stick to this because we kind of know how to talk about things a bit more clearly. All right. So now let me introduce kind of my own notation. We'll say that, I'll make this general. Let's say that GOXY is the set of geodesics between X and Y. The reason I want to make this clear is because I think in Phil's lectures, he used geo to refer to the intersection of all geodesics, whereas here I'm referring it to being the collection of all geodesics. Okay? So just a slight distinction there. Okay. And then let's recall, once we make these assumptions, some of the things we learned in the courses last week. So first of all, if I take a passage time between 0 and say any one, whatever I say can be generalized to an arbitrary direction. It doesn't have to be E1. But let's just make everything concrete. So I divide by n, then this converges, in some sense at least, to the time constant mu. And here, notice I've not made any extra assumptions on these edge weights. I've just assumed the standard non-negativity. Right? And so all that I get when I make no other assumptions, no moment assumptions at all, is that this convergence happens in probability. And I stress this a little bit because that's all we need. Okay? So we can speak of a time constant, some limiting number, which is finite, does exist. So that's the time constant. All right, let's call some other things. So in this setting where I have the subcritical probability at 0, the collection GXY is non-empty, at least non-empty almost surely. And let me not write a bunch of almost surelys everywhere. This is non-empty for all X and Y. Okay, so I can actually talk about geodesics. So I can actually talk about their empirical measures. Okay. And third, and this is perhaps the most important of these, if I take a geodesic, let's say gamma n, so this is going to be a geodesic between 0 and any one. So whenever you see gamma sub n in this talk, it means some geodesic between 0 and any one. And suppose I take, well, this is my notation for the number of edges that I use. So I'm thinking of gamma n as a collection of edges, as a set of edges. So this is the cardinality of that set, i.e. the number of edges used. And what we learned in that is that if we have the subcritical probability assumption, then this gamma n in length is bounded almost surely by some large constant for all large n. So this is for all large n. Okay, so geodesics are linear. There's some weak version of geodesics being straight. Okay, so geodesics take a linear length. So when I divide by n, right, I'm kind of getting back to an order 1 quantity in the passage time, but I'll have the same thing when I divide by the number of edges in my empirical measure. So this keeps everything in the realm of order 1. So I can actually talk about limits. All right, so any remarks, questions, clarifications? Interrupt me at any time, of course. Okay. So what is the object I'm interested in? Interested in this object I called the empirical measure. And all this is a definition to make that histogram precise. Okay. So for a path gamma, I can define this for any path, not necessarily geodesics. We define a measure, which I'll write nu gamma. And nu gamma is a probability measure that's obtained by summing over all of the edges in gamma of the Dirac delta measures at the edge weights. So this records that histogram in the notation of a measure. Right? So I have some, well, let me make sure everything's precise. This is the Dirac delta measure. So it places mass 1 exactly on TE and all 0 on all of the real numbers. And I'm just taking some linear combination, in fact, a convex combination. I'm dividing by this length of the geodesic so that it corresponds to exactly how many terms are in this sum. So this is a valid probability measure. Right? So I'll point that out. This is a probability measure. I've chosen my normalization by dividing by the length of gamma exactly to ensure that. Okay. Questions about that definition? Just want to make sure that's absolutely clear. All right, so now I've stored the information of what edge weights the geodesic uses in the form of this measure. Right? So if I know this measure, then I have at least a knowledge of what proportion, not necessarily how many, but what proportion of edges we're taking the low, medium, or high weight edges, or if you can imagine continuous distributions, whatever edge weights you used in there. Okay. So this is the object that I'm interested in. And the question that we ask about this object goes back to Hoffman, or at least this was the first instance that I'm aware of it being written down. So Hoffman asked, if gamma n is a geodesic between 0 and any 1, and I look at its empirical measure, so I look at nu gamma n. So now I'm actually focused on the empirical measures associated to geodesics. And the question was, does this sequence of measures have a weak limit as n goes to infinity? So does this sequence of measures converge weakly? And if that's the case, what that means is that there's some unique combination of low, medium, and high weight edges that gives me the right balance to achieve the optimal passage time, right? In some macroscopic sense, right? So if indeed there is a limit here, it means there's some optimal strategy. There's a unique optimal strategy for getting to 0 to any 1. Okay. Questions about what the problem is asking? Right, so just to review, make sure we are all again on the same page. What this means, so i.e., we want that for all bounded and continuous test functions, test function f, we want that the integral of f of t, nu gamma n dt. So if I integrate f with respect to this measure, it should converge to f integrated against some limiting measure. So this nu is my limiting measure. And that's the object I want to at least claim might exist. And at the time of Hoffman's question, we didn't have a single non-trivial example of a law L for which we actually knew that this limit exists.
So,
I don't think it's on.
Maybe now. Yeah, okay.
Is this convergence supposed to be uniform among all geodesics of length n?
Yes.
Or are you talking about a specific sequence of geodesics?
Right. So you're imagining the case when I have a non-unique set of geodesics, right? So there's more than one geodesic. Of course, that will, in fact, almost surely be the case when I have discrete weights.
Right.
Right. So I'll make a definition to make that clear, but just very quickly, yes, I demand that this should be true for all geodesics. The question becomes much harder to ask if I want that, well, I'm going to choose a specific sequence of geodesics. How do you choose that sequence? And then you might get a limit that depends on the sequence. So let me just, for the sake of kind of slicing through all of those ugly cases, I will insist that if this question has an affirmative answer, what I mean by that is that this limit will not depend on the sequence that you've chosen. And every sequence you've chosen will have a limit, and it will be this one.
And the rate of convergence, is that supposed to be uniform among all geodesics as well, or?
Not necessarily.
Okay.
No.
So each sequence is going to have the same limit,
yeah,
but not necessarily in a kind of uniform way. Okay.
Other questions? And again, I'll make a definition in a moment. But first, let me define some bit of notation that will allow me to not write a bunch of integral signs throughout the talk. I'm just going to write this as f integrated against nu gamma n in this kind of inner product notation. So this just means I always have a test function f and a measure, which out here in the case is nu gamma n. It could be any measure. That just means integrate test function against measure. What I really want is that this converges as n goes to infinity to f integrated against some limiting measure. That's what I want. So here's my definition that exactly clarifies what I mean by an affirmative answer to Hoffman's question. So let us say that L, remember this is the law of the edge weight distribution, belongs to some good set. So this is the set. I use script P to remind you it's probability measures. And I'm going to write P empiric, so P imp for P empirical. If almost surely for all choices of gamma n belonging to a set of geodesics between 0 and any 1, we have that nu gamma n, the empirical measure associated to said geodesic, converges weakly. So this is my notation for converges weakly to some limiting measure nu, which is deterministic. Almost surely, I want to converge when I choose any sequence of geodesics in this weak topology to the measure nu. That's what I mean by an affirmative answer to Hoffman's question. As I said, when Hoffman asked this, we didn't have a single non-trivial example. Okay. Questions about what that means? Okay. So let me pose a related question before we kind of talk about how to approach Hoffman's question. Related. And here, for the sake of being kind of historically accurate, I will attribute this to Michael in the same conference. So this was part of an AIM conference back in 2015 that Hoffman posed this question. And Michael kind of reiterated, put this question back into the discussion. Does gamma n divided by n in its length, so does the number of edges that gamma n uses divided by n converge to some constant lambda deterministically? Constant deterministically. So I can, in addition to asking whether the empirical measures converge, I could ask whether their lengths when I scale by n converge to some deterministic constant lambda. And the reason I kind of say, Michael reintroduced this into the literature is that this question actually appeared in the work of Hammersley and Welsh in '65, the one that got FPP started. This question is as old as FPP. Okay. So let me now state one more. Let me write one more definition. Put it on this board, and I'll try to save this board. So let us say that L belongs to the good set of probability measures, P length. And then I'll call this equation star, this length question. If star holds, almost surely, star holds, almost surely for any choice of the geodesics gamma n. So here you choose any gamma n in the set of geodesics between 0 and any one. And you want that their scaled lengths scaled by the linear quantity n converge to a deterministic constant length. So this is like a law of large numbers for the geodesic length, which we might hope for because we know that geodesic length is bounded by a linear quantity. Questions about either of those definitions? So I've got two versions of what I mean by a good distribution. I've got the good distributions with respect to this empirical measure question. I've got the good measures with respect to this length question. And my claim is that these two are related. Go back over here. Okay, so here's my claim. Is that P empirical is a subset of P length. P empirical is a subset of P length. So if I can answer affirmatively in the P length question, it doesn't tell me anything about the P empirical question, but the reverse is not true. If I have an affirmative answer for P empirical, it gives me answers for P length. Okay, so let me just prove this, or at least give you a rough proof sketch, the idea. Okay. So suppose that L belongs to P empirical. Okay. And then let gamma n be a geodesic that you choose. Of course, doesn't matter which one by my very strong definition of what P empirical means. Then if I want to write T of 0, any 1 divided by n, well, this is a geodesic, so I can just rewrite this as T of gamma n divided by n. Okay. Now here's where the notation comes in handy. So recall that inner product notation where I integrate a TIFR function against the measure. Notice this is just integrating the measure, let's do it, nu gamma n against the identity function. Because if I integrate an empirical measure against the identity function, I just sum the weights that I've seen along that empirical measure. Now there's a little bit of a caveat that here I've divided by n, whereas in the empirical measure, as I defined it, the normalization was of the length of gamma. So actually what I need to do is multiply here by the length of the gamma to cancel out that normalization over there and divide by n as I'm dividing by n by here. Okay. But notice this is exactly the quantity that you're interested in if you want to answer whether L belongs to P length. Okay. So now what we can say is, well, gamma n divided by n, let's rewrite this as now gamma n divided by T0, or T of gamma n. And then I've got n divided, or T of gamma n on top divided by n. Okay. So I've got two factors here. So I've just put in this extra factor of T of gamma n. This factor, in some sense, at least weakly, converges to the time constant mu, because that was passage time between 0 and any 1. On the other hand, by this calculation, I know that this can be related to this inner product notation, integrating the identity function against this. Right? So with this now, this is exactly, right, if I take some limit, this converges to integrating the identity function against nu, where nu is the limit. So here nu gamma n converges weakly to nu. And then here on top, I've got the mu. Right? So here, the reason I've reversed it is because notice T of gamma n was on the top here, T of gamma n is on the bottom here. So this limit of these test function notations comes here on the bottom, and then I've got this time constant on the top. So this is my lambda. And the reason why I used P length was exactly in assuming that this guy converges to that guy. Now there's a little bit of a catch there. The identity function, it is a continuous function, but it's not a bounded function. But it's not the most unbounded function. Right? So it might be believable at least that if I had some weak limit here, that it actually, the test function integral actually worked for the identity function as well. So that's why I say it's a proof sketch. It's not completely precise. Questions about this?
Yeah, so are there examples that show that this is a strict containment in your claim?
Right. I think, yes, I certainly believe it's a strict containment. Whether or not I could argue that rigorously is a different question. part of the issue, as you'll see, is that by the end of the talk, we'll have shown that P empirical is indeed dense among all probability measures, but I can't name any explicit element of it. So it's actually pretty hard. It's not hard to identify things that don't belong to P length. Therefore, it's not too hard also to identify things that don't belong to P empirical. But identifying something that belongs to P length but not in P empirical, hard. Other questions? Okay. So unlike the P empirical question that Hoffman asked, we actually know something about the P length question. This is back due to Hammersley and Welsh. And 65. And maybe they didn't show this in like 100% generality that I'm assuming here with no moment assumptions, but the argument is kind of robust once you have modern tools. So here's the statement. So remember I fix my law L of the edge weight distribution, and then I'm going to have this notation where I say L plus H. And what is this? It's the law of the edge weight distribution, but just adding a constant H. So I just add a constant H to all the edge weights. Okay. And then the statement is, for all but countably many H, and here I'm going to slow down a little bit and write it's all but countably many positive H. This is, if I write negative H, right, maybe some of my edge weights take the value 0, and then when I decrease now I have negative edge weights. That's a little bit of a problem. You can get away with it for a very, very small H, but let's just assume H is positive so I don't run into any of those issues. Okay, so for all but countably many H that are positive, we have that L plus H belongs to P length. So what this means is I can take arbitrarily small perturbations of L, right, where I'm just adding a constant H, and it's because it's only countably many of H that are in the exceptional set. I can take H arbitrarily close to 0. So I take arbitrarily small perturbations of my original edge weight distribution, and then I recover something that has a positive answer to the length question. Okay. But of course, we're left with, if I have an L that I'm very interested in, this doesn't tell me about the case when H equals 0. Okay. And so this example, this argument of Hammersley-Welsh, it gives me a large family, and in effect, a dense family among all probability measures on the non-negative numbers, a dense family of things that belong to P length. So P length is dense among all probability measures on 0 to infinity. But what I don't know is that actually I have any examples for which the edge weights can take the value 0, or even if they can take some values arbitrarily close to 0. Because as soon as I add an H, I've pushed all of the edge weights to some fixed number bounded away from 0. So I don't have good examples of P length, at least vis-a-vis this question, where the edge weights can take values arbitrarily close to 0. But the Hammersley-Welsh problem at least gets us started. Tells us that this P length question is not an absurd question to ask. And if P length is dense, maybe there's kind of hope that P empirical is dense. Right? We actually haven't seen so far that it has any non-trivial elements, but the punchline of this talk is that P empirical is dense among all probability measures. All right, questions about any of that? This is the basis of where we're going to start. Okay, but before I get to the methods, let me point out some counterexamples. This kind of goes back to Evan's question. So counterexamples to belonging in P length or P empirical do exist. And if you thought about this question for a little bit, it's not too hard to come up with these counterexamples. It's a little trickier to make the arguments precise. So here, let me kind of punt those arguments, the work of Arjun with Rasmussen and Timos Balanin. This was 21, I think. Correct me if I'm wrong. Okay. And here's an example that would be falling within the work of their paper, which does a whole lot more than these counterexamples. But let's just study this part. So suppose my edge weight distribution takes two values. It takes the value 1 with probability 1/2, or it takes the value 3 with probability 1/2. Okay? So about as simple as an edge weight distribution as you can come up with. Well, occasionally you could kind of believe that there's only 2 edge weight values here. Occasionally you should believe that if I have this geodesic, say coming like this, so here the geodesic comes into this vertex, and suppose the path of this geodesic is like this, comes out like that, and suppose that these 3 vertices are all, or these 3 edges are all weight 1 edges. It's believable that occasionally the geodesic is going to make some move like this, and there happened to be actually a weight 3 edge lying there beneath this little plaquette. Okay, well, if I'm in this scenario, it doesn't make really a difference to the geodesic whether I take the 1, 1, 1 or the 3. So I could have this alternative route of just following the 3. And if I change my geodesic, instead of following these 3 1s to following a 3, I've decreased my length, right? I've changed 3 edges to just 1. And I've also biased my empirical measure towards 3. So no longer am I placing the weight of these edges on 1, I'm placing the weight of the single edge on 3. And if you encounter this a macroscopic number of times, so if you encounter this little picture along the geodesic, an order, so let's say at least epsilon times n many times, then you can argue that this distribution, so this L, does not belong to P length. And it doesn't therefore belong to P empirical either. Okay. Believable? So in fact, the argument that this paper kind of makes precise, among many other things, as I said, is this kind of argument. It's got to encounter this little environment, macroscopic number of times. When I say macroscopic, I mean order n. So this actually makes this problem more interesting from my perspective, because it's not just this boring answer of everything belongs to these sets. Right? In fact, we've got these counterexamples that make the problem a little trickier. Any questions about that? Again, just interrupt me at any moment if there are questions.
Are there any known continuous examples?
Say that again?
Are there any known continuous counterexamples?
No. I would not be surprised, let me not pose it as a conjecture, but I wouldn't be surprised if whenever you have a completely continuous distribution, it has to belong to P empirical. But no, continuous is much harder to work with. The reason why this is kind of nice, I mean, it's kind of not in P length for somehow a silly reason, right? It's kind of you're violating uniqueness. So as soon as you assume the geodesics are unique, maybe this kind of eliminates all these kind of weird scenarios. Right? And going back to Evan's question, right? You asked, is there an example where it should belong to P length, but not in P empirical? Right? Well, you could come up with an example like this, where in fact, you have these sort of situations, but it's not like a 3 edge versus 1 edge trade-off. It's a, say, 2 edge to 2 edge trade-off. So suppose I have some environment like this, where I see a 2, 2, and then I see a pi and a 4 minus pi. Okay? Now, the reason I choose pi is because now this is irrational. And so I can't hope to kind of recover some combination of the 2's that somehow changes the length. Right? Now, I haven't worked out the details of this, but I think this might be an example. Right? And this example also shows that these problems, if I phrased everything in terms of LPP, which can certainly be done, these problems don't go away. Right? So P empirical still won't be full, won't contain all measures in the LPP question either. Other questions? All right. So now, let me actually show a bit about how we can make progress on this question. So I'll spend the remaining time trying to give you some sense of a proof of certain results. All right, so I'm going to change notation a bit. This is my change in perspective. And it's important to keep in mind I'm really doing nothing more than changing notation. Right? And if you just do a bunch of definition chasing, then you can kind of get back to all the original objects. But make sure I am honest and don't let me get ahead of myself and say stuff that I'm going too far with the notation. So here's my change in perspective. What I'm going to do is assume that the edge weights, TE, are realized in a particular way. And this has no loss of generality. So this is without loss of generality. I'm going to assume that the edge weight TE is realized as some function of a different weight. I'm going to call it UE, where UE is an IID family of uniform random variables on the unit interval. Okay, so they're uniform random variables between 0 and 1. And then I'm just taking some function of those uniform random variables, which they were IID, so the TEs will be IID. And this is no loss of generality because you can come up with a nice tau that makes the distribution work. So for example, you could take tau to be the inverse CDF of the distribution L. So that's kind of a standard exercise that works. So I can come up with some tau that makes this distribution work. So the map's uniform to the right distribution. But what I will assume only is that tau, now some map from 0 to 1 to the non-negative numbers, the only assumption I'll make is that it's measurable. So it's important not only that such a tau exists, but that I can kind of choose it arbitrarily as long as it works. So as long as it gives me the right distribution on TE, I don't care what the actual tau is. I just assume it's measurable in the sense of Lebesgue. Okay. The reason why this is important is what we'll eventually do is take this object tau and do functional analysis on tau. So we'll kind of put tau in certain nice spaces. And for those nice spaces, I can't just assume it's always the CDF, inverse CDF of something. I need to make the tau as general as I can. And once I have tau in some nice spaces that I can do functional analysis on, then I can get some results. That's why I want this assumption. Okay. So I just make this assumption, right? It's just a change in notation. And then I'm going to talk about a different set of empirical measures. So instead of talking about the new gamma n's as I was before, I'm going to talk about these sigma gamma n's. And these sigma gamma n's will be defined in very much the same way. I'm going to sum over the edges in this geodesic gamma n. Again, I'm still assuming it's a geodesic. I still take a sum of Dirac delta measures, but no longer are they the Dirac delta measures at TE, they're the Dirac delta measures at the UEs. So I'm just taking the pre-images of all those TEs. And then here's the other change. I'm not going to divide by the length of gamma n, so this won't be a probability measure anymore. I'm actually just going to divide by n. So here I'm assuming that I know the endpoint of gamma n, so this is in the geodesic set between 0 and any 1. So n is kind of implicit, so I can just divide by that n. It's kind of known to me once I know what geodesic I'm talking about. Right? And the reason why this is nice is because now, before, when I was properly normalizing to be a probability measure, I was completely eliminating the information of the length. I couldn't recover the length of the geodesic. Whereas now, if I take the test function, which is just the constant function 1, and integrate against sigma gamma n, well, now this is just taking the number of e's that I see in the length of the geodesic, this is the length, divided by this constant that I put here, n. So now I can recover, if I store my information in terms of these sigma gamma n's, I can actually recover notions of length. That's one advantage. The other advantage is that I can still recover the passage time from all this, right? Because I can just push forward all of the UEs back onto the edge weights. So for instance, if I integrate the test function tau against sigma gamma n, well, what is that? That should be, well, I'm just taking tau, applying it to all the UEs. Well, those are the TEs, I add them up. That's the passage time. So it's the passage time of gamma n divided by n, and here I'm assuming gamma n is a geodesic, so it's the passage time between 0 and any 1. So just by integrating sigma gamma n against this kind of fixed measurable function, I can recover all the passage times. So there's no loss of information here. Okay. Questions about this notation? Okay. Let me come back over here. And now with this change in notation, I'm just kind of rewrite all of our finite quantities and their limits in terms of these sigmas. So suppose again, I start with T0, NE1, divide by n. I know in some sense this converges to the time constant mu. Right? Okay, so this T of 0, NE1, I just told you this was now, okay, so let me write out just to emphasize what's going on. Let me write out, this is an infimum over all paths gamma between 0 and NE1 of T of gamma divided by n. That's just by definition. And then let me use that bottom test function notation to rewrite this as an infimum over gamma between 0 and any 1 of tau integrated against sigma gamma n. Or sorry, sigma gamma. So again, just nothing but rewrite. Nothing has happened yet. All right, so let's actually give this name, this kind of set of sigmas that I realize in this way, a name. I'm going to call this Rn. And R, I used R because I think of it as realizable. Okay, so these will be the set of sigma that are realizable from a path between 0 and any 1. So it's just a set of sigma sub gamma such that gamma is a path between 0 and any 1. Notice I'm not restricted to geodesics. I can take any path. So this is a random set of measures. And in fact, because I've chosen a different normalization, I've divided by n. This is a random set of super probability measures. So in fact, all elements of this set, except for one, will have mass strictly greater than 1. Okay, so this is a mass of super probability measures. Okay. Questions about that? So now if I rewrite in terms of this, it's the infimum over sigma belonging to this set Rn. Again, it's just definition chasing of tau integrated against sigma. Anything unclear? Okay, very good. So now this is a random set of super probability measures, but where do these super probability measures live? They live on a compact set. They live on 0, 1 now. Right? So this is nice because if I take, for instance, the space of probability measures on a compact space, that's itself a compact space under a nice metric, say the Wasserstein metric. Well, I have a slight complication. This is not the set of probability measures, it's a set of super probability measures, and their masses could be unbounded if I take a very, very long path. But I know that if gamma n is a geodesic between 0 and any 1, then that means that the mass, so let's say the test function sig1 integrated against sigma gamma n, by our assumption, this is at most c. C was some fixed constant. So now here's where I use the linear scaling of geodesic lengths. So ultimately what you can say is that, well, really in the geodesic sense, I only care about measures that have at most mass c. And the measures that have at most mass c on a compact set, that returns to being a compact space. So what that means is that any sequence in that space, I can take subsequential limits. So now take some gamma n, and here let me write gamma nk just to remind you this is a subsequence, such that, and here this is a set of geodesics between 0 and n sub k times E1. And now we take some subsequence such that sigma gamma nk, as k goes to infinity, converges weakly to some sigma, let's call it infinity. So there I've just kind of applied some, compact abstract result. I have something in a compact space, right? All the geodesics have mass bounded by at most c, so I can take any sequence of geodesics. There's some subsequence among those that has these sigmas converging to some weak limit. But wait a minute, if I took those sequence of geodesics, they were always achieving this passage time, and I was always dividing by n by my choice of normalization. So this, when I integrate those guys against tau, it should always return this time constant sigma, this time constant mu. So this now should converge to tau integrated against sigma infinity. So now what I've done is I've expressed this time constant mu as an integral of that measurable function tau that I just fixed from the beginning against this abstract measure sigma infinity. Such some sigma infinity works. Okay. Now we're almost done with this kind of picture. The thing that remains to be seen is that, well, wait a minute, I only did this for the geodesics, right? But if I take any sequence of paths that have bounded linear length, then I can perform the same sort of iteration, right? I take some subsequence of paths, and then I can take some subsequence of their associated sigma measures. And then again, I can get something where I have a linear functional integrated against tau. And this step, I'm using the weak convergence. And well, all of those such paths wouldn't have done any better than the passage time. So in fact, what I can say is any of those such sequences would have been at least this value. And so what I can actually write this limit as is an infimum over a new set of measures, let's call them sigma infinity, and some R infinity set. And now I have to tell you what R infinity is. And really all R infinity is exactly what I need it to be in order for this statement to be true. Because what did I just do in this R infinity set? I just took all possible subsequential limits of sigmas associated with paths between 0 and any 1. So R infinity, just in words, it's a set of all subsequential limits of elements in the Rn sets. Now that's a bit imprecise, so let me actually clarify. This is a set of all sigma such that the limit, as n goes to infinity, of the distance. So here this distance is some metric on measures. Again, maybe take the Wasserstein metric. Distance between sigma and Rn. And I want that this limit is equal to 0. So I can find some sequence of measures in the Rn sets, where n tends to infinity, that I can approximate this sigma. And then I have exactly this variational formula. So let me copy it down over here. This is the central tool. Mu equals the infimum over sigma infinity belonging to this R infinity set of tau integrated against sigma infinity. Questions about what I've done there? This is almost rigorous. If tau is continuous and bounded, this is basically a proof. If tau is not continuous bounded, now you have to do a bunch of approximations. There's a lot of steps you have to recover, but that's the idea. Are there any questions, remarks about that? Okay. So it's always nice to express whatever law of large numbers result you have, in this case mu, the time constant, in terms of a variational formula. Variational formulas just tend to be very useful, right? In statistical mechanics or in FPP, LPP, all these sorts of things. Okay, so I like this variational formula, but there's one problem. The constraint set, that is the set from which I'm borrowing all of these sigma infinities, is a priori a random set, right? Because it's, well, I took it to be all subsequential limits of a bunch of random sets. So, you know, if I don't know anything else, there's nothing telling me that this R infinity set couldn't be random. So here's my theorem 0. I write theorem 0 because it's really the thing that precedes all of the theorems we really care about. So theorem 0 is that there exists some set R. So this is a subset of super probability measures on the unit interval, such that with probability 1, R infinity equals exactly this set R. So in fact, this very large abstract set, this R infinity set, has an almost sure value. So what that means is that I can delete this R infinity set and just put that deterministic set R. And this makes sense because, well, my time constant certainly isn't random, right? That was completely parameterized by, completely determined by the law of the edge weight distribution, which in itself was completely determined by whatever this measurable function tau that I picked. So as soon as I know tau, then it's a deterministic function to get back to mu. So of course, I shouldn't expect something random here, at least not something random that would change the result. Okay. Now it might surprise you, just doing all this definition that, well, you have this complicated construction, this set R being a deterministic set, that might be a little bit surprising. But the proof, when I sweep all of the details under the rug, is the Kolmogorov-01 law. Again, I've got got all of these IID random variables floating around. And everything I'm taking is n going to infinity, so I really don't care about what happens in any finite box. That's not going to change the values of these limits at all. Okay, now making all of that precise is technical. You have to impose the right topology and embed this R infinity set in the right space. But all of that is just technical. Really, there's no loss of intuition in just saying Kolmogorov-01. Questions? Okay. So now this is very nice, because now I've expressed the time constant as this variational formula. And this variational formula is exactly the infimum of a bunch of linear functionals acting against tau. Right? For every measure sigma in this R set, I'm just acting it against tau in this linear functional kind of way. Right? And what do we know generically? The infimum of linear functionals is concave. And this is actually going back to one of the exercises we saw at the beginning of last week, where we asked about any regularity properties of the actual passage time function as a function of the edge weights. And you would have seen, if you complete those problems, that, well, it's an infimum of linear functionals, right? Because I'm summing just a bunch of linear things for each one of the possible paths. And, well, that's generically a concave function. Right? And if you kind of draw yourself a picture of some concave function, you can convince yourself it exactly is the infimum of all of its tangent lines, all of its super differentials. Okay? So it's just kind of a standard fact. And moreover, it's the infimum of all of its super differentials, right, appropriately shifted. But moreover, any minimizer is a super differential, or a super derivative of this. Okay. So whenever I see a minimizer to this variational formula, what I'm really looking at is a super derivative, right? So here in this concave function, just kind of a generic one-dimensional picture, right? Here I have many super derivatives. And that's because the associated variational formula with this function is not uniquely minimized there. But on these sets where the function is differentiable, I have a unique superderivative. Therefore, I have a unique minimizer. So uniqueness of the minimizers is one-to-one correspondence with the idea that you have a unique superderivative, or let me just write differentiability. Differentiable. So whenever this function, which maps the measurable function tau to its integral against some set, or let me write to mu tau. This is a concave map. And wherever it's differentiable, we know that there must be a unique minimizer to this equation. But wait a minute, where did the minimizers come from? The minimizers came from subsequences of geodesics. So whenever there's a unique minimizer, there's a unique limit to the empirical measures associated to geodesics. So this last question, right, if I retrace all of this uniqueness of minimizer implies an affirmative answer to Hoffman's question. That means that L belongs to P empirical. It doesn't actually go the other way. So the lack of differentiability at some places doesn't tell you the absence of things in P empirical, but this is at least the direction we want, to show existence. Questions about any of that? So this part, I just kind of breezed through some general concave analysis, convex analysis, not going through the details. But there's good news, right? Now I've just said, well, whenever this map is differentiable, I have L belonging to P empirical. That is, there's some unique minimizer. And the good news is, well, at most places, a concave or convex map is differentiable. At most places, we have differentiability. Now, this statement depends, of course, on what space I'm talking about. Right? So if I have a concave function in one set, at most places means a different thing than a concave function in a different. Right? So now here, let me just remind ourselves of what the associated results are. So let's say that I have a particular domain of my concave or convex function. And then there's some degree of differentiability that I can conclude just by completely black box results. So for instance, we all kind of know, remember from our analysis class, that if the domain is the real numbers, then the differentiability that I can assume for such a function is everywhere except at most countably many places. So at most countably many bad points. And what does this remind us of? Well, this looks an awful lot like the Hammersley Welsh problem. Why is the associated domain R there? It was because I was perturbing by a single real number, that H. That parameterized this time constant in terms of a domain of R. And so when you do that, you recover differentiability everywhere except countably many points, and that's exactly the Hammersley-Welsh problem. There's kind of a proof that doesn't go through all of this machinery, of course, but that's really what's going on. Now, if I upgrade R to some multi but still finite dimensional Rn set, then we know that the differentiability that we can conclude is almost everywhere. So on a set of Lebesgue measure 0, I have non-differentiability potentially, but almost everywhere I do. And furthermore, if I have this is the result that, at least when I was searching for it, I did have to look up. It wasn't like I just remembered offhand. But if you have a separable Banach space, and you have a concave function on that separable Banach space, then the differentiability you can assume is that it's differentiable on a dense G delta subset. So there's some dense being the key word. Remember, I claimed that this P empirical set was dense. There's a dense G delta subset of this separable Banach space on which the concave function has to be differentiable. Okay. So now what I'm going to do is conclude with a couple theorems that emphasize how you use this or this. Okay. I'll leave those definitions up. So Hammersley-Welsh uses that first one. Let me give you an example for each of the other two. And all of these results, the two that I'm going to show you, do show that P empirical is dense, but they show it's dense in stronger ways, one from the other. Okay, so theorem 1. So theorem 1 is the following. Fix any probability vector. What I mean is fix any positive numbers, P1 to P capital N. That capital N is the same capital N over there, such that you sum all the PIs, you get 1. So I just have some probability vector. Then the result is then for almost every vector T1 to T capital N in the set of positive numbers raised to the nth Cartesian power. So I take n positive numbers, and for almost every choice of those n positive numbers, we have that the associated distribution. So this is now, I'm going to define my L that I care about, is the sum over I from 1 to n of Pi delta Ti. So this is the edge weight distribution that takes the value Ti with probability exactly Pi. And for almost every choices of the Ti's, this belongs to P empirical. So what this says is that among all discrete distributions, right, with any, or finite discrete distributions with any of these P's, because you get to pick the P's, but the theorem picks the T's, you have that this associated measure belongs to P empirical. So this is one version of density. This already tells you that P empirical is dense among all probability measures in some weak metric. No, Lebesgue almost every. Lebesgue almost every. And it's really, once you kind of have your variational formula, it's just definition chasing through that black box result about concave functions. Other questions about theorem 1? Okay, all right, now let me describe theorem 2. And now I'm going to use that last result. And there are more ways to use these things. If you kind of keep coming up with different Banach spaces to apply it, you can come up with all sorts of examples. All right, but theorem 2 is that fix any measurable function tau. So tau is just that fixed measurable function we started with. Then there exists a dense G delta subset of the following space. Now, it's not exactly a Banach space. It's kind of like half of a Banach space of k times continuously differentiable functions from the unit interval to the positive numbers. Okay. I can find some dense G delta subset of that. And this has the uniform norm on it. So it's dense with respect to the uniform norm summed over all of those k derivatives, right? So I have uniform norm on all k derivatives. And there exists a dense G delta subset such that for every phi in this dense G delta subset, so let's call this dense G delta subset d sub tau for dense. For every phi in d tau, the push forward of uniform on 0, 1. What did that mean? The push forward of the UEs. So all that I'm going to do is now describe for you a slight change in the measurable function tau. Instead of mapping forward the UEs by tau, I'm going to map forward by tau plus phi. So if I change my measurable function to this slight perturbation of tau, and that is no problem because these functions took positive values. So I'm not creating any negative edge weights by this. So under tau plus epsilon, and I just did the push forward of these uniform random variables, this belongs to P empirical. And the reasons why this is nice include that, well, if I started with tau, which was a smooth function, well, now I've just perturbed it by a quite smooth function, right? Not infinitely differentiable, but CK, right? So I can come up with examples where the measurable function tau induces a measure belonging to P empirical, and it's also K times continuously differentiable. Or I can choose K. It also produces examples because, remember, this was on the uniform norm. So these phi's in a uniform norm sense have arbitrarily small uniform norm, right? So for any epsilon, I can find a phi in this set with norm less than epsilon. So I can make arbitrarily small L infinity perturbations to tau. So whenever you have like a horrible tau to begin with, you're going to have a horrible tau after the perturbation. So you can come up with edge weight distributions in this set that have, say, no moments at all, that have the worst tails you've ever seen in your life. There are examples in P empirical. Okay? And as I said, there's more ways of using, especially this Banach-based result, to construct more examples. All right, so I'll conclude with one final point, is that these results, while I enjoyed having them, they don't actually produce any explicit example. So one of the results that I quoted, the exponential LPP, which was James Martin, Alan Tsai, and Ling Fuzhan's result, that actually produces in the LPP context for exactly the model that Martin was talking about last week. An example where we do have empirical measure convergence. But of course, that's using interval techniques. It's a completely different thing. Right? This only is a very soft result. It says we have a bunch of measures that all belong to P empirical, but I can't name a single one. I'd really like to be able to. Say uniform edge weights, uniform on 0, 1. Does that belong to P empirical? I don't know, but I think it should. So there's lots of questions, lots of interesting hard questions that result from this. If you'd like to ask me about them, please do. Thanks for your attention.
Questions for Erik, and I'm keeping an eye on the Zoom chat if someone asks a question online. Yeah, go ahead, Krishnan. Is there a microphone up there? No, it's, yeah, okay.
It works, I think. For some specific TE, you don't have even examples? No?
No, I mean, I can tell you some, like I said, with this kind of example with the 1, 1, 1, 3, I mean, that gives you something that's for, kind of silly reasons not in these sets. But maybe you could kind of like, choose in some averaging way, average over all geodesics, and maybe that almost surely has a deterministic limit. Right, so I don't know that those examples couldn't be recovered in some sense, but at least by the strong definition that I took on that farmost board, they don't belong in that set. But no, I don't have an explicit example other than trivial ones, right? Like just take a edge weight distribution, which is constant, right? Other than those, I don't have a specific example that belongs to these sets. But I can construct examples that have very nice features, that have infinite support, that have subs, they're all supported on the rationals or something like that. But I can't name an explicit one.
Okay, further questions? Yeah, go ahead.
So for the property P length, can we consider different directions than E1? Because in your counterexample, it seems like in an other direction, the property will be true. So is there any counterexample of this property in all the directions?
Yes. So the result that I said before, that works in all directions, right? Now, your question still raises an interesting point, is that I've made these definitions direction specific, and it's not immediately clear if it's true in one direction, it has to be true in all directions. And I kind of suspect that wouldn't be like implausible, but I don't have an argument for that. So these results are always direction specific. We can make the direction any direction you'd like, but they're always direction specific.
Okay, thank you. Anybody else? One more time for Online questions? Okay, if not, let's thank Erik again.
Thank you.